Right, physical science. Here's a video on how to calculate potential and kinetic energy. So here's a pumpkin. We'll start with potential energy. So imagine I'm got this pumpkin and I'm gonna raise it to different heights. Now when I raise this to different heights, I'm affecting how much energy is stored in this pumpkin. So imagine if I say lift it to my head height, which is not quite 2 meters, and I drop it. If my foot was underneath or your foot was underneath, you would feel a lot of energy transferred to your foot and it would hurt. Now, if I was to only drop it from like a height of 1 meter and it hit your foot, you'd feel less energy transferred. So the amount of potential energy that's in this object depends on three things. Depends on how high the object is. It depends on the mass of the object, right? A heavier pumpkin, one that's twice as heavy, is gonna transfer more energy. So the mass of the pumpkin matters. And then how much gravity is pulling down on the object. So here is the formula. Potential energy right? We're going to say PE. It's measured in the units of joules, and joules is our energy unit. Well, that's equal to the mass of the object in kilograms times the gravitational acceleration, which is 9.8 meters per second squared on Earth, and then the height of the object, and that needs to be measured in meters. So for example, if I was calculating that pumpkin that I was showing, potential energy would be 1.0 kilograms times 9.8 meters per second squared times a height of, we'll say 2 meters, and that would be just above head height, so like about here, okay? And so if I multiply 1 times 9.8 times 2, I get 19.6 joules, okay? What happens if I say lift this up to 4 meters, which I can't quite reach? Well, if I change that to 4 meters and I multiply, then that comes out to, what is that, 39.2 joules instead. So, and again, in my calculator, I just typed in 1 times 9.8 times 4. I multiply them all, and that comes out to 39.2 joules. Okay. What happens if I calculate the potential energy for pumpkin 2? This one is a 2 kilogram pumpkin, okay, twice the mass. Well, of course, going to change M. G stays the same, 9.8 meters per second per second. And let's say, again, I'm holding this above my head. Well, then that would come out to 2 times 9.8 times 2. Type it all in. That comes out to 39.2 joules. So, because this is twice as heavy as this one, if I hold the lighter one, the one with less mass, if I hold it twice as high, then these two pumpkins have equal potential energy. So it would transfer the same amount of energy. Now, I know the area of the pumpkin might have hit your foot differently, but dropping these two pumpkins to the ground, right, on your foot, or measuring how much energy is transferred to the ground, they would transfer the same amount when dropped from these heights, okay? You can also ask yourself, let's say I wanted to design some kind of, I don't know, way to store energy, or this is how dams work. We store a lot of water up high. Let's say I wanted to store a certain amount of energy up by either stacking pumpkins or moving mass to different places. But let's take the big pumpkin and let's say, how do I store 100 joules of energy in this by lifting it up, right? And so what I'd be doing is asking, what is the height have to be to find the potential energy of 100 joules. So here's the formula. These are all multiplied. Okay, with a little algebra and some rearrangement, I can say that the height is equal to the potential energy that I want divided by mg. And so I could say put in 100 joules. Say I wanted to get this thing really, a lot of potential. then this would be 2 kilograms times 9.8 meters per second squared. Okay, I'm going to multiply the denominator first. Comes out to 19.6, and that's a kilogram meter per second squared. And so when I divide a joule by that 19.6, or 100 joules by 19.6, I get, oops, let me type it in my calculator, sorry, 5.1. So I would have to lift this pumpkin up 5.1 meters, okay, which is probably getting close to 20 feet. It's somewhere between 15 and 20 feet. I'd have to lift it up 5.1 meters to get 100 joules of energy. Okay, so I can solve that potential energy equation for height or for mass by a little rearrangement. So height equals PE over M times G, or M equals PE over H times G. Those may be some useful formulas, but really the one that we want you to use is the potential energy is the mass times gravity times height. Okay, now back to the small pumpkin. So I can also measure the amount of energy in a moving object. So instead of just lifting this thing up, I can actually throw it, and this would give you the same effect, right? That adds energy to the system. I could throw this at my foot, I could throw it at the wall, and when it hits, it transfers a certain amount of energy. And that depends on two things. It depends on how heavy the object is. So, right, throwing a heavier object will impart more or add more energy to the system. Or throwing an object really fast, okay? So the velocity also affects how much energy is in the system. And so for kinetic energy equals 1/2 times the mass times the velocity squared. So M is still mass, that's still in kilograms. V is something new, it's what we talked about a couple weeks ago, right? That velocity, and we're going to measure velocities in meter per second. And you'll notice this squared, right? I have to square or multiply velocity by itself. So, oops, there's the squared. And then kinetic energy, all energy units in here, when we're talking kinetic and potential, we're going to measure them in joules. So, here you go. Let's say I take the small pumpkin, 1 kilogram, and I can throw this one, let's say, 5 meters per second. So that would be, I don't know, about 15 to 20 feet per second. And I can't really let go of this because I don't want to hurt my house, right? If you guys want to see an exploding pumpkin, you can go back to that video where Mr. England and I were throwing it off the roof. But let's do this. The kinetic energy of the small pumpkin, 1/2 times 1.0 times 5 meters per second squared. Now, when you calculate kinetic energy, you do have to do this in the proper order, right? So this is why you study this in your math class. And so we're going to do that exponent first. So 5 squared, 5 times 5 comes out to 25. You don't necessarily have to worry about the units when we're doing this, but I'm going to show them in here. So 5 times 5 comes out to 25. Then I need to multiply by 1. And then I need to multiply by 1/2. So this comes out to 1/2 times 1 is 1/2 times 25 is 12.5. And since I did everything in kilograms and meters and seconds, right, it comes out to 12.5 joules. All right, so let's say I was, I don't know, I'm working out and I can throw this pumpkin even faster. So let's say I could throw it 10 meters per second, which would be about 30 feet per second, which might still be reasonable actually, but I double the velocity that I throw it. So instead of throwing it 5 meters per second, I throw it 10. We can calculate, let's double the speed, right? We can calculate how much potential energy or kinetic energy is in it, sorry. So I do 1.0 kilograms. I still have 1/2, but this time it's going 10 meters per second. and I'm going to square it. So this one comes out to a half times 1 times 10 times 10. I do first, that's 100 meters squared per second squared. And so I'm going to drop the units. As long as you're in meters, kilograms, and seconds, a half times 1 times 100 comes out to 50 joules. So here you go. If you compare the old one and the new one, right, I double the velocity that I can throw this thing. This comes out to 4 times the energy. Okay, so when you speed an object up, you're actually changing the energy, we say, by the square, and it all comes down to that exponent. Okay, now what happens when you double the mass? So let's take the big pumpkin. Say I can toss this thing 10 meters per second, so I'm doubling the mass this time. What's that going to do to my kinetic energy? Oops. And I'll say double mass. So this time, instead of 1.0 kilograms, I'm going to use 2.0 kilograms. But I'm still going to throw this 10 meters per second. So same speed as the last one, but now double the mass. I get a half times 2 times 100, right? And this one comes out to a half times 2 is 1. 1 times 100 is a 100. Okay, so doubling the mass, going from here to here, doubling the mass, this time doubles. If you compare it to the 50 joules, it doubles the energy. Okay, so mass is important, but it doesn't change the kinetic energy as much as the effect of the velocity would. Okay, a big change in velocity will lead to a really big change in kinetic energy. Okay, and that has to do with this formula. All right. Okay, so here's a calculation that we're going to do that's related to the lab that you guys watched Mr. England set up. So my question is, how fast will this pumpkin be going if I say drop it? And let's do it reasonable so that you guys can kind of see what's going. Now I'm not going to let it hit the floor, but let's say that this is a height of 2 meters. Okay, how fast is this object going right before it hits the ground? And so this requires us to work with both forms of energy, potential and kinetic. And so we're going to go through how to solve a law of conservation of energy problem. Okay, so this pumpkin starts up. Oops, that's a really bad pumpkin. Okay, this pumpkin starts with, there's its center of mass. Here's the floor. Height is equal to 2 meters. Gravity is pulling down and accelerating at 9.8 meters per second squared. Okay, it has a mass of, let's say we did the large pumpkin. So this mass is 2.0 kilograms. And I want to know right before it hits, what's its velocity? All right, so when you start off, I was holding this thing. Let's assume that I'm holding it still. So its velocity is 0. It's got no kinetic energy. It's all potential energy at the top. And at the bottom, when it's touching the floor right at the last moment, then we're going to say it's all kinetic energy and no potential energy. So what's happening is we're transferring potential energy to kinetic energy. So what we can say, the law of conservation of energy says 100% of that potential energy has to be transferred, right? Because you can't create or destroy energy. So it's being transferred to a different form, right? It's moving from potential energy to kinetic. So if we want to say this, the potential energy at the top is equal to the kinetic energy at the floor. Okay, we're going to assume that there's no air resistance, that we're not moving air particles or having to deal with a lot of air particles, because that does affect things. But for this calculation, we're just going to say that it's all kinetic energy at the end, and we can solve this out. So let's solve for the potential energy first. So that would be mgh. Okay, and I'm just going to work one side at a time, just to show you this. We will show you a little trick in just a second, but mgh, the mass is 2 kilograms. Oops, kilograms. Gravity is 9.8 meters per second squared, and the height is 2 meters. Okay, so mgh comes out to, we said 39.2, and that would be joules. Okay, so there's the potential energy at the top. I'll label it 39.2. And since that's going to be equal to the kinetic energy down here, 39.2, oops, not kilojoules, joules. Okay, then we can take that up to our kinetic energy equation. And remember, kinetic energy was 1/2 times mass times velocity squared. We can plug everything in that we know. We know that the kinetic energy at the end is 39.2. We know that the mass of the pumpkin is still 2. And I'm going to leave the units out. And we know, we want to know what the velocity is. Okay, so we can solve this out. So 39.2 is equal to, let's do some multiplication here. 1/2 times 2 is 1. And I've still got this multiplied by v squared. So, I know this is a little much, but we're just going to solve this together. I'm going to get rid of that 1.0 with some division. Right? I get v squared equals 39.2 divided by 1 comes out conveniently to 39.2. And then to solve this, this takes a little square root, right? And so what we're solving for is the velocity. So the square root of the velocity squared is equal to the velocity. And the square root of 39.2, the square root, comes out to 6.26. Okay, and since we're in meters, kilograms, and seconds, the velocity would be in meters per second. So right at the bottom, the maximum speed that it reaches right before it hits the ground is 6.26 meters per second. Okay, and you're thinking, well, but velocity or gravity is accelerating that thing 9.8 meters per second. Well, it turns out that this free fall from 2 meters down to 0 meters takes less than a second. So it doesn't have the full amount of time to speed up that full 9.8 meters per second in 1 second. Right? It only gets to 6.26 before it hits. You guys, I had misspoke a little bit, and I had put something called a kilojoule. So before I end this video, let's just do this one more time, and I'll show you a little trick. Let's say I drop this thing from a much higher height. Let's say the initial height this time, if I remember, I think we said the gym was 63 feet. I forgot how many meters that was. Let me do a little conversion. 63 feet to meters. So this one we dropped it off the auditorium. It's 19.2 meters. So let's say 19.2 was our initial height. Okay? And we're going to, again, say that the potential energy at the top, so on the roof, is equal to the kinetic energy right before it hits the ground. So, and the pumpkin that we had, I think the pumpkin that we had was a little heavier. It was pretty big. Let's say it was 5 kilograms. But really, it doesn't really matter. And I'll show you. Okay, so first of all, let's calculate the potential energy, m times g times h. So the mass is 5. Oops. The gravity, sorry, my pen's coming disconnected. Gravity is 9.8. When I can write. and the height was 19.2. Okay, so multiplying those 5 times 9.8 times 19.2 comes out to 940.8 joules. So that's almost 1 kilojoule, right? So 1 kilojoule is equivalent to 1,000, 1,000 joules of energy. Okay, so we've got almost 1 kilojoule of energy, and that's going to be transferred to the ground. And the ground, at the kinetic energy at the ground is equal to 1/2 mv squared. So I can plug in my mass, which was 5, and v squared. And so then I do my solving. So 1/2 times 5 is 2.5. And divide by 2.5. Do that to both sides. We get v squared equals 376.3. And then to solve for the velocity, I square root both sides. And I get 19.4 meters per second. So when I dropped it off the roof, right, of the auditorium, by the time it hit the ground, it was actually traveling 19.4 meters per second. Now, it turns out that the mass of the pumpkin, whether I threw a medium pumpkin, a little pumpkin, or the big pumpkin, the mass doesn't really affect the velocity. And I just want you guys to see this. This will be where I wrap up. Both potential, right, the energy stored in location or height, and kinetic, the energy of motion, they both depend on an object's mass. So this one looks like mgh, and the other side looks like 1/2 mv squared. And you can see, since I've got this equation with mass on both sides, it turns out that this is true. GH equals, on pen, 1/2 v squared. And I could have solved this without necessarily needing the mass of the pumpkin. So if you're thinking about how energy is transferred, the mass doesn't really play a huge role, right? It's more the height of the object, the velocities of the object. And this is, right, if you're solving law of conservation of energy. But this formula is probably not going to be as useful as our, see if I can go back and just recap. Kinetic energy equation, 1/2 mv squared, and potential energy equation, mgh. Okay, so I'm going to wrap up the video.